Welcome to Spring LIB.
This is the answer to Chapter 12, problem number 31 from the Smith Organic Chemistry textbook. And this problem asks us to devise a synthesis of this molecule that I've drawn at the top here. So I suppose that would be hexanol, so 3-hexanol. And we're asked to devise a synthesis of this molecule starting from acetylene and using organic compounds containing 2 carbons or fewer, and any other required reagents. Okay, and so we're starting from acetylene. So one common way that we've learned to make new carbon-carbon bonds when we have an alkyne is to deprotonate the alkyne, so with a strong base. So for example, I'll use sodium hydride here. And then we can treat the alkyne with an alkyl halide. And so we are restricted to 2 carbon long chains by the parameters of the problem. So we'll use ethyl bromide, and that's going to give us this molecule. Okay, and so from here, we can do essentially something similar again. So we're going to deprotonate this molecule that we've made with sodium hydride again. And then this time, instead of using ethyl bromide as an electrophile, we're going to use this epoxide electrophile. We're going to use this oxirane. And so that's going to get us to this point. So I'll switch to skeletal notation here. 1, 2, 3, 4, 5, 6, 7. Okay. And so now all we need to do is do a reduction of this alkyne to an aldehyde. And since we want the a reduction of this alkyne to an alkene, I think I said aldehyde. And so since we want the trans version of this alkene, we'll use sodium metal and ammonia, so a dissolving metal reduction or a Birch reduction. So sodium metal in liquid ammonia is going to give us our final product here. Okay. Yeah, and so that's how I would approach this problem. So deprotonate with a strong base and then use ethyl bromide to add 2 carbons to our chain here. Do the same thing again, but use this epoxide electrophile instead of ethyl bromide. Now we have our 6 carbon chain with an alcohol on it. And then we just need to reduce that alkyne to a trans alkene. And that's the answer to Chapter 12, problem number 30.